Welcome. In this video, we're going to do Chapter 6 on multiple regression models. And what it does is it extends the results we saw in Chapter 4 on the bivariate regression model where we had y and a single x. Now we're going to have a y variable and a whole bunch of x's that are able to explain it. And in the next chapter, in Chapter 7, we'll look at hypothesis testing. So that will extend Chapter 5. There's some new issues that arise in multiple regression models, such as joint hypothesis testing that we'll get to soon enough. Let me try to motivate multiple regression from the example we've been looking at so far. So we've been looking at a model that was test score, was equal to beta 0, some constant, plus some other constant beta 1, times class size, and let me index these with I like we've been doing, plus some error term, ui. And so, first thing is, I've been using size as short for class size. The book uses STR for student-teacher ratio, and I want to use the same notation on the video that the book uses. I'm going to go ahead and switch from size to STR, but they're the same thing, so don't let that confuse you at all. Okay, now when we actually ran this regression, we got a coefficient of minus 2.88. If I remember right, the standard error was 0.52. That was highly significant in terms of being different from 0. The t statistic there was very, very large, near 4, over 4. That's way bigger than 1.96, so this was a significant effect. And so if you're an administrator, you might think, oh, okay, if I lower my class size by 1 by hiring more teachers, which is costly, I can raise my test scores by 2.88 on average. And so, gee, that looks like it would be a good idea to do that. You could make a cost-benefit analysis that we have to hire more teachers, that's the cost, the benefit is better test scores, is that cost and benefit worthwhile? But at least now we can characterize precisely what the relationship looks like. Or can we precisely characterize it? That's the issue. We talked that there may be a variable we've left out. In fact, there's a whole bunch of variables we've probably left out. Other things besides class size that might cause test score. For instance, average income in the district. If that goes up, you might see test scores going up because wealthier districts can have higher, schools are often funded from property taxes, so maybe you have higher property taxes, you can pay more teachers, get better teachers. You can, as I talked about last time, the parents can do fundraisers amongst themselves. And in this district my kids went to, they hired music teachers and science teachers because they weren't satisfied with what the school was providing. You can hire tutors after school, have special classes. Maybe one parent doesn't work, so you can have more opportunities through there for help at home with homework and other sorts of things. So there's all sorts of reasons why we might think that higher income might have an effect on test scores, independent of class size. Now, it might also be that when average income goes up, the student-teacher ratio goes down because wealthier districts can afford smaller class sizes. Okay, but the true effect, so this is going to mess up this regression coefficient, because what could be happening is it might be that the student-teacher ratio actually has no impact at all on scores. What we're seeing in the data is that it's really average income that's the causal factor. So that's what causes test scores. And what we're actually seeing is when STR moves, it's not because it's moving because average income is changing. So what's really going on is average income goes up, STR goes down, and then you see test scores going up at the same time. So if you have a variable with just a model with just these two variables in it, it will look like when STR falls, test scores goes up. But what's really happening is you're just picking up the correlation between income and STR. Income is really the important factor, but because these are correlated, whenever this moves mostly. There's a strong correlation between those, and we'll show later that in fact in the data that we've been looking at there is such a correlation. Then this coefficient is going to over-represent. It's going to make an effect that's too large. It's going to say that class size has an effect larger than it actually has on test scores, because part of the effect is not actually the class size, it's average income in the district. And there might be other things too that have a similar effect, and we'll come to another thing in just a moment. So the lesson here is that omitted variables, if you leave variables out of your model, that can bias the coefficients. That can give you misleading answers. It could lead to misleading policy. You may go out and hire a bunch of new teachers thinking it's going to affect your test scores, when really test scores have no effect whatsoever. It's really parental income that's the important factor, and the administrator has no way to affect the income in their district. And so that would have been wasted money. And so we have to be careful to add into your model all of the important things that affect test scores. And income's not the only thing. We'll come up with some other variables as we work through the next few chapters to show that we can make this model much richer. Okay. So what we're talking about is called omitted variable bias. So we're going to look at omitted variable bias, see what that's all about. We'll use that to motivate the fact that we need more than one x in our model. So then we'll extend the model to allow for more than one variable. And then once we've done that, we'll look at the sampling distributions of the coefficients, just like we did in Chapter 4. We'll do a little bit on what's something called multicollinearity. And then in Chapter 7, we'll go on and look at hypothesis testing and confidence intervals. Okay, so let's look at omitted variable bias. Oops. So that's the main topic right now, omitted variable bias. And I'm going to use the books example. We'll add income to our model later, really we will. But let's think about a different variable this time. The book uses immigration. So the argument here is these districts are in California, and for some school districts within California, immigration is a huge factor. It's a really important factor in terms of now immigrant kids aren't any less intelligent or anything like that. That's not the argument we're going to make here. That's not why test scores go down. It's their English proficiency. A lot of them are non-native English speakers. So we're not actually going to measure the amount of immigration. We're going to measure the percent of students for which English is not their native language. And those immigrants, those are mostly going to be immigrant students. They may have had poor schooling in the past. Where they came from, they may not have even gone to school. So not only might they have language disadvantages, they might have past educational disadvantages as well that lead to smaller test scores. And so let me make sure that what I said here is right. In terms of the variable we're going to add. Where is it? Well, let's just, yes, percent English language. Yeah. Okay. So, so we're going to add this variable percent English speakers to try to capture that effect. Because so this is just like the average income variable we were just talking about. Suppose that when the percent of non-English speakers goes up, you tend to see class size go up as well. And you also tend to see test scores go down. So not only might class size be picking up the effect of parental income, it could also be picking up an effect of the percent non-lingual English. And it turns out there is a correlation here. The correlation is going to turn out to be about 0.19. So a higher proportion of immigrants is correlated with class size. And the correlation is about 0.19. It's not huge, but there is a correlation there. In that case, the class size variable can be picking up. It might look like class size is affecting test scores, but what you're really picking up is the effect of the percent of non-English speakers that are in the classroom. And so that would bias the coefficient, once again, just like we talked about with parental income, on the class size variable. So here's the omitted variable bias. The bias is in the estimation of the coefficient. So omitted variable bias occurs when two things are true. One, the omitted variable is correlated with a variable in the model. So we need class size to be correlated with percent immigrants or percent non-English speaking, or we need it to be correlated with average income. If there's going to be a bias, that correlation has to be there. That's so that we're going to mix up where the true effect is. If there's no correlation, there's no danger that class size is going to be picking up the wrong effect. And the second thing is the omitted variable helps to determine the dependent variable. The dependent variable is y. In our case, it's test score. In other words, it's not just anything in the world we leave out. We're leaving out things that affect test scores. And so the book goes through some examples to see if, let's do this test. Is it correlated with a variable in the model? And sometimes you can just think about it and say, yeah, it's pretty obvious those two things have to be correlated. You don't actually have to even have the data to check it. You can just say, yep, it's pretty obvious those are correlated. And it helps to determine the test scores. So the book goes through some examples to say, would you expect to have omitted variable bias in these cases or not? And the first example is the one we've been talking about, percent English speaking in terms of their native language of the kids. One, we've already noted that it's correlated with STR, so it's correlated with the X, with the variable in the model, and it likely causes score. It likely has a causal effect on score. So you would expect, if you left this variable out of your model, you might wonder if this correlation is actually there, but it turns out it is. Once you know that, then you're going to have omitted variable bias. And so if I leave this variable out of the model, the coefficient on STR is going to be wrong. On average, it won't equal the true value. Okay. Secondly, what about time of day of the test? That probably affects test scores. It might matter whether you give it first thing in the morning or late in the afternoon or right after lunch or right before lunch. Exactly when these test scores are given in each district might affect the test scores. So you can at least tell a story where the time of the day of the test would matter, but hard to imagine that it's correlated with class size. There's just really no reason to think that the time of the day you give the test would have some correlation with how big the classes are. That's just an administrative decision or a teacher decision on when during the day to do it. I don't know, maybe there's some chance those things are correlated. In a bigger class you want to get over with early or something, but this doesn't, it's hard to imagine. So you wouldn't expect omitted variable bias here because you don't have the correlation with the class size that you need. So leaving this variable out would not cause bias in the model. It'd make your standard errors bigger, but it wouldn't have any bias on the coefficient, so that wouldn't be a problem in that case. What about teacher parking? So the third example is teacher parking in square feet in the parking lot or something like that per pupil. Number of parking places, say, for teachers. This is likely correlated with class size. When STR goes up, you need more teachers. So have more parking. See that? So the more teachers you have, the more parking spaces you have. The more teachers you have, the smaller the STR. Oh, arrow's wrong. When this goes down, you have more teachers, so you have more parking. All right, so it's correlated. This is an omitted variable. It's not in our model, and it's correlated with something in our model. So one of those conditions for bias is true, but hard to see how it would cause scores. How would having one more parking lot for your parking space for your teachers affect your test score? Maybe they can't find parking, they come and they have to walk a long ways or something, and they're annoyed, it makes them worse teachers or something like that. But for the most part, it's hard to imagine how teacher parking is going to cause test scores. So although it's correlated, it doesn't cause. The other one caused test scores. The second example we did, it caused test scores, but it was uncorrelated. That was the time of day. This is the opposite. It's likely correlated, but it's hard to see how it's going to cause test scores. So you wouldn't expect omitted variable bias here. So the point is you need both of those two things to be true. You need that the omitted variable causes y. In this case, y is scores. And you need that it's correlated with things that are in your model. The problem, why is there bias if you omit something in this case? It's the first assumption. The problem is the first assumption. That was that the expected value of ui given xi is equal to 0. And we said this is not true when ui and xi are correlated. And so suppose you have a model yi is beta 0 plus beta 1 x. Let me just start writing the way I'm going to write them. 1i, that's the first x, plus beta 2 x 2i plus ui prime. And this thing in parentheses is ui. So you can think of this as being scores, and this as being STR, and this as being percent English language, something like that. Okay. If I leave the variable out, it's in the error term. There's a whole bunch of other things that are in ui prime I'm just not writing out, but we're going to write this one out. So if we leave it out, it's in the error term. And the problem is then that if I run this model, if I run yi equals beta 0 plus beta 1 x 1i plus ui, where ui is this, ui and x 1i are correlated. And that's what causes the bias and the inconsistency. Why are they correlated? Because x2 and x1 are correlated. English language percent and the size of the classes are correlated. And so when this goes up, UI goes up, and you tend to see bigger class sizes. You tend to see x1 going up. So there's a correlation between these two because this is left in the error term. And so whenever there's a correlation between UI, so when we run this model like we did in chapter 4, there's going to be a correlation between UI and x1i. That's going to bias this coefficient. That minus 2.88 is the wrong number. It's a biased estimate of the true causal effect on class sizes. So the problem is this, and more specifically, it's that UI and xi are correlated because UI has the omitted variable in it, and the omitted variable is correlated with the variable in the model. And again, if these, we said one of the conditions was if these are uncorrelated, then if they're uncorrelated, then we don't have a problem because now UI and xi are not correlated. So this will be an unbiased and consistent estimator. The second one was that it causes yi. If it doesn't cause yi, it won't be in the error because it's just not part of the model. And so if it's not in the error, then it's not correlated either. And so it needs to be correlated with this and in the model. It needs to cause yi. And this problem doesn't go away with bigger samples or anything like that. It's a consistency problem as well. And so it's a severe problem because you're getting the wrong answer. We can look at more specifically, we can look at it mathematically as well. So let's look at a formula for the bias for omitted variable bias. Remember from the past, we've already shown that beta 1 hat is beta 1 plus, and I'm going to write this as 1 over n minus 2 times the sum of the xi minus x bar times ui minus, well, u bar is 0, times ui over 1 over n minus 2 times the sum of the xi minus x bar squared. So we worked that formula out when we were looking at whether this was biased or not. And we said as long as x and u are uncorrelated, this is unbiased because this expectation will be 0. If it's uncorrelated, the expected value of this term is 0. Because what this is, as n goes to infinity, this converges to beta 1 hat is beta 1 plus. This is an estimate of the covariance, and as n goes to infinity, it goes to the true value. So plus the true value of the correlation of covariance of x and u over, and this is nothing more than the variance of x. So as n goes to infinity, these two terms, this goes to the covariance. That's just the formula for the estimate of the covariance. With infinite data, the estimate converges to the true value. This is an estimate of the variance of xi, and this is the degrees of freedom thing. And this goes to the variance. Okay. Now recall that the correlation between x and u is the covariance of x and u over sigma x, the standard deviation of x, times the standard deviation of u. That's a formula we did during the review. I can plug in then, that tells me that the covariance of x and u is equal to sigma x, sigma u, times the correlation of x and u. Just multiply this over there. So then I can rewrite this using that fact as beta 1 hat is beta 1 plus, and just sub in for the covariance, sigma x, sigma u. And remember the correlation can be written as rho xu. That's just the correlation. Another term, another way to write it, over sigma squared x. Those I can, this is just the square root of that. So beta 1 hat is beta 1 plus rho xu times sigma u over sigma x. So this is the bias. If I take the expected value here of beta 1 hat, it's only going to be beta 1 if this is 0. We always have error terms, so that's not going to be 0. And x doesn't have an infinite standard deviation. So this term's never going to be 0. So the unbiasedness, so unbiased or consistent requires what? It requires that rho of x and u be 0. And that's what we've been saying. If x and u are uncorrelated, then beta 1 hat goes to beta as n goes to infinity. It's consistent. We let n go to infinity a little while. And we can do this with expectations too, to say, if this is 0, then the expected value of this is this. And so unbiased and consistent, this is what we need. We're not going to have a 0 standard deviation for our error terms. There's always error terms in the model. And again, this is never going to be infinite. So this term's not 0. So we need this to be 0. And that's what it's going to require. So also notice then what this tells us is that the degree of bias goes up if, this is the important one, the correlation between x and u goes up. The more correlated these are, the bigger the bias. This is the bias because we want this to equal this. I should be saying this converges to these. I shouldn't be using an equal sign as n goes to infinity. So beta 1 hat goes to this as n goes to infinity. And if I want it to be consistent, then I need this to be 0, and same for unbiased. But anyway, the degree of bias then is going to be higher if that's bigger, if sigma u is larger, or sigma x is lower. But this is the one that I want to focus on because it tells you that sometimes you'll have an omitted variable because you don't have any data on it, and you can think of a story that as to why it might be correlated with one of the x's in your model. But you're also fairly convinced the correlation's pretty tiny. If the correlation's tiny, then the bias or the inconsistency is also fairly tiny. But if you think there's a high degree of correlation between two variables, you think about it and say, yeah, those are probably really highly correlated. I can see that. Then that omitted variable is going to exert a high degree of bias. Now, the next thing is that the direction of the bias, whether it's biased above or below, direction of the bias depends upon the sign of rho of x and u. Remember, it's between 0 and 1. That's perfect negative correlation, perfect positive correlation. When it's 0, there's no correlation, and so on. We've been through that. So when this is negative, beta 1 hat's going to be below this on average. When this is positive, beta 1 hat's going to be above this on average. And so it depends upon the direction of the bias. For instance, in the example we've been looking at, we know that the correlation between student-teacher ratio and immigration is 0.19, so it's positive. And then the model that we have is score I is beta 0 plus beta 1 times STR, or district I, plus beta 2 times immigration for district I, plus UI prime. And this thing in parentheses is what we've been calling UI. Now, beta 2 is less than 0 because we expect as the percent of immigrants grow up, scores go down. So what that tells us is that when immigration goes up, we tend to see the error term going down, and we tend to see STR going up. This is that 0.19 correlation. And so this is the X, and this is the U. So what that tells us is that the correlation, when U goes down, X tends to go up. The correlation between X and U is negative. And so if beta 1 hat, since beta 1 goes to, as n goes to infinity, beta 1 hat plus rho of X and U times sigma U over sigma X, this coefficient is going to be biased downward. If it's negative, it's going to be too negative. So this imparts a downward bias. But the general point here is that you can tell the direction of the bias by looking at the sign of rho of X and U. Okay. So what that tells us is we need to avoid omitted variable bias if we want to avoid biasing our coefficients. And so what we can do now is, so what's the best thing to do? How to overcome? Add the variable to the model. That's the fixed. And so in this case, we could say yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus ui. Take that thing out of the error term and actually put it into your model. So now run that model where this is immigration, this is STR, and this is scores. And then the population regression, expected value of yi, given x1i equals some value. This is an actual number. x2i equals some value is beta 0 plus beta 1 x1i plus beta 2 x2i. And that's the population regression. The expected value of the error term is 0. And so how do you interpret the coefficients? Well, the coefficients in these models are partial derivatives. The partial of yi with respect to xi, 1i, is beta 1. The partial of yi with respect to x2i is beta 2. So the way you interpret these, if you can't remember what a partial derivative, it's the change in y due to a change in x, holding everything else constant. So what beta 1 is the change in y due to a change in x1, holding x2 constant. So it does that all else equal. Beta 2 is the change in y due to a change in x2 holding x1 constant. So it imposes that all else equal assumption that we need. And so these coefficients are the effect of this variable on y holding everything else in the model constant. So it's as though you've gone into a laboratory and you want to look at the effect of class size on scores, and you're somehow able to hold immigration constant. By putting immigration in the model, it has the effect of holding all that other stuff constant for you. And so those are called partial effects. Now, it's easy to extend this to more than just two x's. And so in general, the way we write the model, I mean, we might want to include a third x, which is parental income, because we already know that probably imparts a bias, because we know income probably causes test scores. And income is probably correlated with both immigration percentages and with class sizes. So we've got an omitted variable that causes scores. It's correlated with things in the model. That's going to bias both beta 1 and beta 2, so we need another variable. Sometimes in some models we'll need even more than 3 or 4 variables. And so in general, we can write yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus beta k xki plus ui. So there's k x's in the model. K is the number of variables in your model. I goes from 1, 2, up to n. And later we'll learn that n has to be greater than k. You can't have less data than things you're trying to estimate. The population line is just the part without the error again. That's the population regression. That's the average over all districts or overall whatever. And UI is the idiosyncratic effect for each district. What else here? The definitions of homo and heteroscedasticity are the same. If sigma squared u is constant overall, it's the same for all I. That's homoscedastic. If it differs, if you have to put an I here, so that you get a different sigma squared for each I, for each district, the variance might be different or each whatever, then you have heteroscedasticity. So there's nothing new in terms of homoscedasticity and heteroscedasticity. So let's turn then to the OLS regression. How do you estimate the coefficients in this model? We're not going to derive formulas for this case because they're too complex unless we use matrix algebra. And you probably don't, most of you don't know. But so how do we estimate beta 0 through beta k? We do like we did before. We minimize the sum of squared errors from I equals 0, or 1, sorry, to n over all the observations, yi minus beta naught hat minus beta 1 hat x1i minus all the way out to beta k hat xki. So this is the error. This is ui hat. That's the estimated error squared. So we're going to minimize, once again, the sums of the squared errors by choosing beta naught hat, beta 1 hat, up to beta k hat. So we're going to choose the formulas for these things that minimize the sum of the squared errors. So it's exactly what we did for the 2-variable case. It's just an extension. And that would give you, so you would differentiate with respect to beta naught hat, beta 1 hat, all the way to beta k hat. So you have k plus 1 equations, and you'll set each equation equal to 0. Remember, we just had beta 1 and beta naught. We had 2 equations, one for beta 0, one for beta 1. That's k is 1 in that case. We have k plus 1 equations. Here we're going to have k plus 1 equations. We set each one equal to 0. Then we solve for beta naught hat up to beta k hat. We're not going to do that. It's too hard. If you use matrix algebra, it turns out to be x prime x inverse x prime y is the vector beta hat. But we don't know how to do that. But there's a simple formula in matrix algebra. I shouldn't have even mentioned it. And so that's in principle how you would do this mathematically. And we're not going to actually do it. What you're going to end up doing, they're very tedious formulas. The general case would be too hard to write without matrix algebra. It would just take the whole board, and you can hardly do it. So what you do in this case is you put your data in your computer. You'll have the y variable, x1, x2, x3, say in an Excel spreadsheet. Tell the computer, here's the data, y, x1 through xk. Estimate the coefficients. You push a button, and it does it for you. So let's apply this to the test score example. So remember that our original model was score hat. The estimated score is 690, the estimated model 698.9 minus 2.88 times the student-teacher ratio. What we're going to do is we're going to add the percent English language, the percent that have English as their native tongue. Okay? And then we're going to re-estimate. When you do that, you get that score is 686.0 minus 1.10 times the student-teacher ratio minus 0.65, sorry, times the percent English language. That's the book's notation. So notice that originally we had a coefficient of 2.88, minus 2.88. Now it's fallen to minus 1.10. So that's an indication that we did in fact have that bias towards more negative numbers that we said we had, we predicted we had, because we knew this was positive, was correlated with the test score. And so you can see the bias in the coefficient that you get if you don't have this variable in the model. You're going to think that test scores, that class size has a much bigger effect on test scores than it actually has. What about the measures of fit in multiple regression? How do we assess whether we have a good or a bad fit? There's not going to be much new here. It's just a generalization of the ones we looked at before. So we're going to look at the standard error of the regression, what we've been writing as SER. We're going to look at R squared. Those are what we had for the two-variable model. And we're going to add a new one called adjusted R squared. And that's often called R bar squared. So let's start with the standard error of regression. So the SER, which you can also write as S of U hat, the estimated standard error of the error terms, that's the square root of S squared U hat. That's the estimate of the variance of the error terms, where S squared U hat is nothing more than 1 over n minus k plus 1 in parentheses times the sum from I equals 1 to n of the U I hat squared. And another way to write that is it's the sum of squared residuals over n minus k plus 1. When we did this for the two-variable case, this was n minus 2. And we said we subtract off 2 because we have to estimate two things, beta 0 and beta 1. We call that a degrees of freedom correction, and we explained why we needed it. All we're doing is extending the degrees of freedom correction to the multivariate case. Now we have beta 1 through beta k, that's k things, plus beta 0, that's k plus 1. So we're estimating, so this is just a degrees of freedom correction. And so the way you estimate the standard error is just the sum of the U hat squared. Remember that U hat I is just the difference between Y and its predicted value. That's our prediction error. That's what we predicted, that's the actual value, and that's the one. So nothing much new there. As before, the interpretation of this will be in y units. So the standard error will be in units of y. So if y is points on a test, the standard error will be points on a test. If y is measured in inches, the standard error will be in inches, and so on. So the units of the standard error of the regression are the same as the units of your y term. Okay, r squared. Again, it's the same as before. And the intuition is identical. So you can go back at the end of the one video, and then I redid a little more on the second video for chapter 4 at the very beginning on r squared. R squared was just the explained sum of squares over the total sum of squares, where the explained sum of squares was the sum from I equals 1 to n of the y hat I minus y bar squared. That's the amount of the variation you're explaining. We drew a picture in the second video for chapter 4 to show that. And the total sum of squares is just the deviation of y from its mean squared added up. And so nothing new there. You just find y hat from your predicted model. Y hat is beta naught hat plus beta 1 hat x1 plus beta k hat xk. Find the y hats, and then just find these two things, and that gives you r squared. And it's a measure of the goodness of fit. Remember, it's between 0 and 1. And as r squared gets closer and closer to 1, that's an indication that your points are closer and closer and closer to your estimated model. And the same thing's true here. Now, often, r squared is used to assess if another variable should be added to the model. We're going to discourage you from doing this, but I want to explain that this thing r bar squared is. So often what people will do is they'll add a variable to the model. They'll look at what happens to r squared. If r squared goes up by a whole bunch, they'll say, okay, that's a variable that ought to be in the model. Now, often that's not the best way to assess if a variable should be in the model. You should look at theory, you should look at the t-statistic, you should look at other sorts of things. It's possible that r squared won't change much, but it's highly significant with t's, and there's other complications. But sometimes it's used this way. But the problem is, when you add a variable, r squared always goes up. It can't go down. Theoretically, it could stay unchanged, but it can't possibly ever go down when you add another variable to the model. And so if it always goes up, how are you going to know if you need to add a variable or not? So let's think of it. Let's look at it this way. Here's yi is beta 0 plus beta 1 x1i plus beta 2 x2i plus ui. And I'm asking, should I add x3? And so I run this model, and I run this regression, and I get beta naught hat plus beta 1 hat. I get beta 1 naught hat, beta 1 hat, and beta 2 hat. And that gives me an r squared for that particular model, that fit. Okay. And then I run a new model. yi is beta naught plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ui. So I've added this new variable to the model. If the regression package wants to, so that can always pick the same beta naught hat, beta 1 hat, beta 2 hat as before, and beta 3 hat equal to 0. So this model could always do as well as this model at explaining the data. We're minimizing the sum of squared errors. Remember, the other way to write r squared is 1 minus the sum of squared residuals over the total sum of squared. The sum of squared residuals, I'll have some sum of squared residuals for this model without x3 in it. So I'll get an r squared and an SSR will give me the r squared. This, if I pick this, I will get an identical sum of squared residuals. And so if these are my estimates, I'll get exactly the same sum of squared residuals I got before, and I'll get exactly the same r squared. Now remember what we're doing when we pick our regression coefficients. We're minimizing the sum of squared errors. We're minimizing SSR. And so if it can't do better, it can pick some other coefficients, but if it does so, it has to be able to do better than it can by picking these. If this is the best it can do, it'll pick these, and you'll get exactly what you got before. But almost always it can do even better by letting beta 3 not be 0 and picking different beta 0, beta 1s, and beta 2s. In that case, the sum of squared residuals has to go down because you've got a better fit. It wouldn't pick anything other than this unless it was fitting the data better. If it's fitting the data better, then the sum of squared residuals are going to go down. See, it can always fit the data at least as well as this model by just making this coefficient 0. Then I've got the same model. So it can always have the same sum of squared residuals as before, or it can potentially do better by picking different numbers. And so this either stays the same or it has to go down, and if it goes down, r squared has to go up. So there's simply no way that you can add a new variable to the model and have r squared go down. It always goes up. So that's a problem if we're trying to use this for model selection. So what people have done is to overcome this, they use something called r bar squared, where r bar squared is defined as 1 minus n minus 1 over n minus k plus 1 times the sum of squared residuals. So we add this term in parentheses to the model. And this is greater than 1. So one thing we can say, if this is bigger, the r squared is 1 minus SSR over TSS. Oops, over TSS. Sorry, I forgot a term. If this number is bigger than 1, we're subtracting off something bigger, so it has to be that r bar squared is always less than r squared. And r bar squared can be negative, unlike, it's rare that that would happen, but it's certainly possible. If the sum of squared residuals, you have a really bad model, so the SSR is really close to TSS, this is almost 1, and this is greater than 1, that product could potentially be bigger than 1. If this is near 1 and I multiply it by something bigger than 1, that could be bigger than 1, and then you'd get a negative number. And that's going to happen when actually r squared would be very close to 0. And so it's possible for r bar squared to actually be bigger, be less than 0. So here's the thing about r bar squared. Here's why we did it. If the number of variables goes up, k is the number of variables. So if k goes up, it's the number of variables in your model. So when a new variable is added, the sum of squared residuals has to go down, or it could stay the same, but that would rarely happen. And at the same time, n minus 1 over n minus k plus 1 will go up. This causes r bar squared to go down, or go up, sorry. This causes r bar squared to go down. So on net, it can go up or down. And so what some people do, and again, we'll talk about this in a later chapter, and this is really not the best way, but this is where r bar, adjusted r squared or r bar squared came from, is they'll keep adding variables and so long as r bar squared is going up. But the minute, if you add a variable and it goes down, then they leave that variable out of the model. So they use it as a way of selecting which variables should be in or out of the model. You'll learn, particularly in 421, there's much better techniques and ways to do that. One is to just use your head and think about it, what ought to be in my model theoretically. That's probably a better technique, but there's other ways to do that. But anyway, that's r bar squared, and unlike r squared, it can go down when you add more variables. If SSR doesn't change very much, that's an indication that it didn't do very much when you added it to the model. It had hardly any effect on SSR. If this effect is bigger than this effect, this is like a penalty function. When you added k, this makes r bar squared go down, and SSR has to go down by enough to make that r bar squared actually go up for that variable to stay in the model. Okay, let's do let's look at our example. The test score example. Remember that for the model, when we had score equals beta naught plus beta 1 str plus u, r squared was 0.051. We didn't do r bar squared at that time. When we add in the model score, it's beta 0 plus beta 1 str plus beta 2 times percent English language plus u, r squared is 0.426, and r bar squared isn't much different. It's 0.424. In this case, the standard error of the regression was it 19 point something? What was it? Oh, 18.6, almost 19. Here, the standard error of the regression falls to 14.5. That's still a pretty big number, but it's a big improvement. So this tells us that our predictions will be more precise, and we have a much better fitting model than we had before. Now we're explaining 42% of the variation in y, 43%. Before, we were only explaining about 5%. And so this variable has had a big impact on our ability to explain the test score data. Okay, I'm going to stop this video here, and we'll pick this chapter up with part 2 very soon. Thank you.